Assalamualaikum to
Belum
to
lagi, belum
everyone.
lagi, belum lagi.
Oh yeah, belum. Buat malu
Okay,
pula.
let's go.
Assalamualaikum warahmatullahi wabarakatuh. Uh, we are from group 2. Want to present about let's say synchronous condenser in electrical machine and drive. Okay, we start with introduction synchronous condenser. A DC excited synchronous motor that spins freely with no connection, uh, as known as synchronous capacitor, synchronous compensator in electrical engineering. It is to modify circumstance on the electric power transmission system rather than converting electrical power to mechanical power or the other way around. Installation and use of the condenser are the same as those of big electric motor and generator. For power factor correction in power grid, synchronous condenser can replace capacitor banks and capacitor banks reactive power reduced as grid voltage falls. Uh, although a synchronous condenser's reac- reactive current might rise as voltage falls. And this is a intro for a synchronous motor. The rotation of the shaft in synchronous electric motor is synchronized with the frequency of the supply current as steady state. Multi-phase AC electromagnet on the stator of synchronous motor produce a rotating magnet field that is timed to the oscillation of the line current. The second synchronized rotating magnet field of any AC motor is produced by the rotor's permanent magnet or electromagnet. It comes in various size, ranging from self excite excited fractional horsepower to large industrial scales. Most synchronous motors in the fractional horsepower range are employed in application requiring accurate constant speed. The synchronous motor serve two crucial purpose in large industrial scale with increased power. First off, it is a very effective way to turning AC energy into work. Additionally, it offer power factor adjustment by operating at leading or unity power factor. This is a synchronous motor for the first one, which is a model SE2662-3M. The rating is 0.3 kilovolt, 0.3 kilovolt. And right here is a synchronous motor 2, which is we use a model SE2662-5Q, and the rating is 0.8 kilowatt. I will pass this calculation to my teammate, which is Muhammad Aiman bin Zulkifli. Thank you.
Okay, for the question we have using for the power factor, reactive power, active power, and apparent power. So the for the calculation for power factor, we will use P divided by S. Which mean P is power and S we use as apparent apparent power. Yes, P divided by S. So for the reactive power, uh, we will use S S S power of 2 minus by P power of 2 square root, and that's it. The formula for reactive power, and for the active power, S time by PF. PF mean by power factor. For the apparent power is square root P square of 2 plus Q square of power of 2. So that's for the formula for the calculation power factor, reactive power, active power, and apparent power. So next. Calculation for task 2, same as task 1. We will use the same formula for the power factor, reactive power, active power, and apparent power. Next. So this is the plotted graph that we graph from the power factor SM1 and power factor SM2. This is the graph we get. The uh, voltage and the power factor. Yes, that's the graph we graph. Next discussion. An experiment involving a synchronous condenser, aka a synchronous capacitor or synchronous compensator, which run unloaded, was conducted in this lab by supplying synchronous inertia. This device improved short circuit strength and frequency stability, as well as voltage management and stability to produce or absorb reactive power. Two types of synchronous motor with a different model: three-phase power supply, DC voltage regulator, digital meter, direct online starter, and DC protection. Switch are needed in this experiment. Both synchronous motor have power rating of 0.3 kilowatt and 0.8 kilowatt. However, as is it a three-phase motor, the voltage for both motor is the same at 230 volt or 400 volt. In order to compare the two outcome, we must produce a graph of power factor and field voltage for the SM1 and SM2. That's all from me. Thank you.
Okay, for analysis, we had to measure the power factor, power volt, amps reactive, and volt ampere. We had to take a reading for the first experiment utilizing a synchronous motor with a 0.3 kilowatt power rating by using synchronous condensation, which operates without a load for the first experiment. And outcome for the power is in increasing disorder. It was also discovered that as the excitation voltage rises, the demand power over ampere falls. The second experiment required us to obtain a reading utilizing a synchronous motor with a 0.8 kilowatt power rating, and the outcome for power is also in increasing disorder. As the excitation voltage rises, the demand power over ampere in this experiment is decreases. There are several discrepancies. When using 0.3 kilowatt as opposed to 0.8 kilowatt, the upper rise is smaller. This is as a result of the power disparities that the two motors may supply for distribute being different. This experiment demonstrates the variation in power losses while employing synchronous motor of various rating. For the conclusion, synchronous machines are composed of synchronous generators and motors. The advantage of an AC system versus a DC system are numerous. Therefore, the AC system is used for all phases of the production, transmission, and distribution of electrical energy. Synchronous generators or alternators are the components that convert mechanical energy into alternating current, electricity. The same machine is referred to as a synchronous motor if it may be used as a motor. Synchronous machine in their simplest form are motors or generators whose field current is provided by a different DC power source. That's all from us. Thank you.